Hey, good morning, everybody. This is Chris McTaggart, your presenter for today. Again, on behalf of DTE and Consumers Energy, we are continuing with the Building Smart Energy Efficiency Essentials for Modern Homes series. And today we're going to be focusing on the building enclosure, aka the building envelope, and specifically talking about the role of insulation and the proper installation of insulation in modern homes here. So we got a long presentation today. We've got lots to cover. So I'm just going to go ahead and jump right into it, starting right now. So what we're going to do today is cover uh, basically what is the building envelope. If you've never heard of that term before, what exactly are we constituting as the building envelope or building enclosure? And what is the role of insulation? Why do we insulate homes? And, I think for a few of you, you may consider some of this material to be, I'd say, a good refresher on things that you already know. But I'm hoping that everybody takes something away from this presentation that they can really put into action to make homes better here in the state of Michigan, because comfortable, resilient, airtight, well insulated homes, that's really kind of good for everybody. I think being from Michigan, living here in the Detroit area, we got a lot of old homes, and people kind of grew up with lack of comfort and expecting to have high energy bills. But moving forward, with brand new construction, we have an opportunity to really set up the state for success going into the future with better homes that really have a quality building enclosure, a quality building envelope with good quality installed insulation. So we'll talk about, just kind of the fundamentals of insulation. Why do we do it? What different materials are there, etc. And then we'll talk about some different assembly specific opportunities. So talking about different opportunities for insulation in walls versus in floors, slabs, roofs, etc. And then we'll talk a little bit about where we stand with the energy code today, with its expectations for insulation, and then get into our above code programs, which is really, like we've been talking about. It's kind of the theme of this whole series. How do we go above the existing code to do even better? So again, if you didn't attend the session a couple weeks ago, my name is Chris McTaggart. I am the co-principal and president of Building Efficiency Resources. We're a national resident quality assurance and training provider. I myself am based in Detroit, Michigan. This is my hometown. And we have raters across the state of Michigan, over in the west side of the state, some in the northern part of the state. And I've been all throughout Michigan throughout my life, checking out homes as well as just the natural beauty of our state. And so I know a good bit about how we may want to implement these practices, not just in Southeast Michigan and not just in Southwest Michigan, but really throughout the state. Okay, so building envelope. What are we talking about? Well, the building envelope is basically how we define the boundary of living space, more or less. So the six-sided box, if you will, that defines our conditioned, insulated, airtight living space of our home. And so we can think of the building envelope as being the building shell or the building enclosure. Um, you could call it the pressure boundary, the thermal boundary, thermal enclosure. They all kind of mean the same thing, in essence. So in the diagram that we have on the right, this home has a living space on the first floor, the second floor, and the third floor, and it has an unconditioned basement. So we have our pressure boundary or our thermal boundary or our thermal enclosure or our building enclosure or our building shell. They all mean the same thing. They're basically at the floor is the frame floor over that unconditioned basement. Then we have our walls that go up the first floor, second floor, and then even the gable end walls, it looks like, for our third, an unvented roof assembly, so as to basically make the attic part of conditioned space. So again, this term conditioned space is more or less saying, well, these are parts of the building enclosure, that we are intentionally trying to keep comfortable for inhabitants. Um, Sometimes they're directly conditioned. So, like, our first floor of our house, our second floor of our house. Well, generally speaking, that's where living spaces are going to be: kitchens, bathrooms, bedrooms, offices, etc. And then you may have places like basements that maybe they could be indirectly conditioned, meaning maybe there's not direct conditioning to those spaces, but they are still considered to be within the building enclosure, more or less. So, by code, we're defining conditioned space as an area or room of the building that's served by heating and cooling systems to maintain space, space cooling and heating conditions. Conditioned space boundary is the principal air barrier and thermal barrier, basically, for the home. So, take that basement again. Well, maybe it's directly conditioned, or maybe it's not. But if our primary air barrier and thermal barrier is at those basement walls, then it's probably part of generally conditioned space. So moving on here to other things to consider. So pretty much always bedrooms, kitchens, bathrooms, etc. Those are our main living spaces. Those are pretty much always conditioned space. Attics could be, if you had, say, like a spray foamed roof line or otherwise a unvented attic space, where then the attic becomes part of conditioned space. Again, it may be directly conditioned, it may be sort of indirectly conditioned, but if it's part of that building enclosure, thermal pressure barrier, building envelope, then we're kind of considering it part of conditioned space. Basements, same deal. And that happens a lot in Michigan. Oftentimes we have unfinished basements that are either sort of semi-conditioned. Ideally, you'd throw a register or two down there to directly condition it, just to kind of keep it at a similar temperature as the rest of the house. But regardless, oftentimes basements, especially here in Michigan, we've got basements that are, generally speaking, within conditioned space. And then same thing for crawl spaces. Crawl spaces may be a little bit more rare in new construction today, but they certainly are being installed. And I would say it is an emerging trend, perhaps more so than ever before, to encapsulate those crawl spaces, to make the crawl space part of conditioned space, to make them part of our building enclosure. And the reason why is because crawl spaces tend to have a lot of moisture in them that come up through the ground. And so in a lot of ways, it's better to go ahead and have a really airtight barrier at the floor of the crawl space. Same thing up the foundation walls without vents, and then to seal and insulate those walls and the rim joists of that crawl space so as to bring the crawl space into conditioned space. The value there too is that oftentimes ducts and air handlers may be included in a crawl space. And then, basically, if you have any duct leakage or heat loss off of those ducts, that's basically occurring in conditioned space instead of just being wasted into a vented crawl space. Rarely, garages and porches are conditioned space. Not never. Technically, by the code, garages sometimes are conditioned space. If you've got direct conditioning to them, they can be included within conditioned space by code. Now, when you start to get into HERS ratings and above code programs, generally speaking, we're not including garages within our definition of conditioned space. Porches depends. Is it a conditioned sort of 4-season porch, or is it an unconditioned 3-season porch? My house, for example, I have, quote unquote, a Florida room, a sunroom that is attached to my house, and it stays comfortable enough, but it's not directly conditioned, and therefore it is not part of conditioned space. We would consider it more like a 3-season porch. Okay, so the building envelope is supposed to be the combination of a air barrier as well as a insulation layer. Ideally, you want both together. You want your peanut butter on top of your toast. You don't want it separated because those two are just so critical to have together. Why? Well, if we just have an air barrier but no insulation, well, you may have air tightness, but you're not really going to end up having comfort, associated with having insulation, which stops conductive heat loss. If we have insulation but no air barrier, well, there's a risk of what's called wind washing, where basically, we have air that is going through the insulation, and that actually reduces its effectiveness. And we'll see why here in a little bit. But so take this image here. We've got that is a air sealed attic plane in a vented attic space. And so we can see that an electrical box has been air sealed and top plates have been air sealed. Well, that's perfect because now we can go ahead and blow some insulation in on top of all that, or possibly bat it. I would probably blow it just because it's hard to split those bats around those framing members and those wires. So I'd probably just go ahead and blow in some fibrous insulation, whether it's blown fiberglass or blown cellulose. And we're going to be in good shape then now that we have an air barrier, that sealed drywall plane, within our insulation on top of it. That's the combo that we're looking for a building envelope. So, our various insulated assemblies, we've got vented and unvented attics. We have various types of wall assemblies, and rim and band joists, kind of like a wall assembly. They're kind of treated like walls, generally speaking, but they're a little bit more tricky to get perfect. And then slab and floor assemblies. And we're going to show all different types of examples of these. And again, I'm sure many of you all have kind of been there, done that, especially if you're a HERS rater, but we're going to hopefully give you something to take home to your builders so that you really understand sort of the value of considering, potentially some upgrades when it comes to insulation layers. Okay, so, but to understand that, we at least got to talk about, why do we insulate homes? Well, we want to save energy. Obviously, I think this is becoming a bigger deal here in the state of Michigan. Our utility rates have gone up. And, that has for a lot of reasons. The utilities are modernizing the grid. They're modernizing their ability to be able to meet the demands of the state. And as a result, they have to make those investments, and they have to justify that economically. So, we have rates that have been increasing here in the last few years in the state of Michigan. So I think that energy savings and dollar savings matter a lot. Obviously, there's an environmental principle too. Michigan, we're very proud of our environment in Michigan. We're the Great Lakes state. We've got all these great bodies of water and farm fields and forest lands that we want to conserve, and making sure that they stay ecologically more integrated and pollution free would be ideal, right? So that's one of the main reasons why we insulate homes, because we want to save energy, which has both an economic benefit, a grid benefit, as well as a benefit to the environment. And then beyond that, humans need to be comfortable. Imagine a world where energy was free and or extremely inexpensive, and we didn't use fossil fuels at all. And so let's imagine a world like that. Well, would we just not insulate homes then because we didn't really care about the energy savings? Well, no, we would still want to, because insulation makes people comfortable. And we are a heating dominated climate. Michigan gets cold. We all know that. We just went through a very cold, longer winter here in Michigan. Well, if you were in an uninsulated home, man, you probably had some pretty high energy bills that hit home in your sort of budget for your homestead, as well as you probably weren't that comfortable and maybe felt kind of drafty and just felt uncomfortable, like there was a lot of, sort of drafts and loss that were coming off of your body. Well, that's because, insulation helps to make buildings feel more comfortable because you retain that heat and you improve basically the surface temperature of the building enclosure, which then ends up meaning that you have, less heat loss off of your body because we're warm. Human beings, we're about 100 degrees, 98 speaking, we want to keep our houses at like 70 degrees. Well, that means we have this thing called radiant heat loss off our bodies. We're actually going from, we're the warm thing and we're losing that heat to the surfaces that surround us through a process called radiation. I won't get too nerdy about that, but it's a big deal. That's why people feel uncomfortable when they're close to, say, a single pane window, is because it's not necessarily draftiness like wind blowing in. It could be, but usually it's actually the feeling of heat being sucked off our bodies and radiated into that, uninsulated, glass assembly. Same thing if we have poorly insulated walls or a poorly insulated attic or poorly insulated basement walls. Same kind of deal. It's not going to feel as comfortable as if we had a fully insulated building enclosure. So primarily we use insulation to reduce what's called conductive heat transfer. Conduction is basically heat loss through surfaces. So we warm up our air inside of our house, usually in Michigan with furnaces, but could do it with a heat pump or a boiler perhaps. And say we heat up that air to 70 degrees. Okay, well, those molecules of air then interact with the surfaces of our building enclosure, our roof, our wall space, our basement walls, etc. And so then that heat energy wants to conduct through those building assemblies. Insulation slows down that rate of conductive heat transfer. Insulation is not specifically used for air sealing or reducing convective heat transfer, which is the movement of air. Some insulations will do both, such as spray foams. If spray foam can both be an air barrier as well as an air sealing product. But it's important to understand that insulation generally is not for air sealing. It's really for reducing conductive heat transfer. So it's also interesting that the way that insulation works, it's counterintuitive. We're actually trapping air inside of an insulation product. And that's what ends up reducing the rate of heat transfer. So it's that trapped airspace inside of those insulation products that end up actually promoting greater R value and therefore less conductive heat loss, which is, again, very counterintuitive. Let's take a fiberglass bat. Well, fiberglass bat, you don't want to go and compress it, smush it into itself. Why? Because those specifically designed, engineered pockets of air that are trapped in the insulation, when you compress it, now you just have the fibers in touch with each other, and therefore it actually promotes more heat loss. You might say, well, that doesn't make sense because what about, like foam board insulation? That's very dense. Doesn't that mean that, that basically the foam is just pushing through? No, but the foam has very tiny little microscopic air pockets. And that's why foam tends to have a higher R value than other insulation products. So basically, we want to make sure that when we're installing insulation, we understand why it's supposed to be installed correctly, because it actually has a function. However, the manufacturer recommends to install it, there's a reason behind it. You probably heard of fiberglass bats, higher density bats. Again, those higher density bats that give you, instead of an R19, they give you an R21 in a wall cavity. Well, the reason why is because in the same, 5.5 inches of insulation, it's not that they've compressed the insulation, it's that they've made the pockets of air smaller or denser, which ends up promoting greater resistance to heat flow. So all of this is probably a little bit beyond the scope of what we need to talk about today, but us as HERS raters, we get into some really nerdy stuff about equations, physics calculations for heat loss. And, R values can be used in order to calculate that heat loss. We can just kind of do it manually, more or less. And so, the way that this equation works is, number one, R values can be turned into what are called U values. It's the inverse. So basically, if you take 1 divided by R, you get the U factor, which is the rate of conductance. And so you take that U factor times the area of that assembly times whatever your delta T or your temperature difference is, and that will allow you to be able to calculate the BTUs per hour of heat loss. You can do the same thing by just doing the R value underneath. So if you don't want to convert the U factor from an R value, you can just basically put the R value underneath. So let's take, the top assembly here. We've got an R5. And so we end up basically putting it through this equation, and we get 5,000 BTUs per hour of heat transfer, versus if we had an R10 assembly, it cuts it in half. Why? Well, because our U factor was basically cut in half as a result. Instead of it being a 0.2 U factor, it's a 0.1 U factor, and therefore there's less. But for the total assembly, then we have a heat flow of 7,500 BTUs per hour. So this kind of gives you a little bit of kind of a simple way of looking at how to calculate this rate of heat loss. So getting into cavity versus continuous insulation. Cavity insulation, it's what's within that framed assembly. Continuous insulation, it's what goes over the entire assembly. And so for cavity insulation, it's important to install it properly. So, basically without gaps or voids, cutting around wires and plumbing and any additional framing that may be in the way. You want it to be installed with minimal compression, because again, the way that insulation gets its R value is purposely through, we're talking about bats in this way, through basically, being installed at the thickness that they were designed to be. If we compress them, then all of a sudden they're going to perform at a worse level of performance. For bats, you could have unfaced or faced stapling of bats. It doesn't really matter. Obviously, if you do faced bats, then stapling on the sides would be a good thing, basically so that we maintain the insulation in substantial contact with the drywall once it's installed. So different insulation products, really ranges here. The main conventional ones that we see are fiberglass bats, obviously the most popular product. They have good economies of scale. They tend to be a little bit more tricky to get installed perfectly. Blown fiberglass is an alternative that could be used, and successfully in above grade walls as well, through a system called the BIB system, or a blown fiberglass wall system. Blown cellulose is an option. Mineral wool is basically a non-combustible sort of mineral or rock wool, as oftentimes it's referred to as. Has some other properties, but it can be used as an insulation product. And then we've got low and high density foam products as well. High density foam, again, that higher density gives us a higher R value. And again, you can see that there's ranges for these products. You may say, well, how does that make sense? Well, because let's take fiberglass bats. There's low density fiberglass bats that don't trap as much still air, and there's high density bats that trap more still air. You can blow in cellulose with a relatively higher rate of air within the mix, which ends up making it fluffier, but it means it traps less air, versus we can dense pack it, and then again, we're trapping more air within the fibers. So that's kind of how that works. In the ResNet system, we look at grading insulation, so the installation of insulation. The rub here is that for grade 1, that's the best. We're basically trying to get assemblies that have cavities that are full, side to side, top to bottom, front to back, that really have almost no gaps or voids, and then very minimal compression. And if you do have compression, it's only like, 3/4 of an inch of the intended thickness. This makes it kind of tricky for bat products to uniformly get this, not because there's anything wrong with bats, it's just that they're hard to get kind of perfect within a cavity, especially when you have things like wires, plumbing, or additional framing members in the way. Grade 2 might be more realistic for a lot of bat products. That's like what I'd consider to be a pretty good bat job would be a grade 2. It means that you have some defects, some missing insulation, but not very much. And then, there's some compression, but again, not substantial compression. Grade 3, lots more gaps and voids, but still not an overwhelming amount. But it just means it's kind of a sloppy job. Maybe bats aren't always cut to fit. Or maybe you blew in an assembly and it's slumping a little bit. And so you get very small gaps at the top of a stud cavity. It's not ideal. That may end up making it a grade 3. Or maybe if you don't have the insulation in substantial contact with an air barrier, that would potentially make it a grade 3 as well. So here's some examples of grade 1, 2, and 3. So, we've got a blown fiberglass. No, it's blown spray foam, it looks like. And, basically, and I'm going to take that back. That is blown fiberglass. So we've got net and blown assemblies here that basically are fully filling the cavity, top to bottom, side to side, front to back. Both for the walls as well as the frame floor over a garage. That looks awesome. That's definitely a grade 1. Grade 2, we see this, it looks like an unvented attic assembly, or possibly they just sort of put in the bats ahead of time for some type of scissor truss. They're installed okay, but obviously around like the can lights, they're not really cut around the can lights so that the insulation will be in contact with the drywall substantially. But otherwise, I'd say that, it's by and large going to fill that cavity fully. And then we got grade 3, we got bats that are installed that are rounded shoulders. Insulation is going to be substantially not in contact, and they're not cut to fit all the way to the top. They're a little bit short. And so that's what makes this a grade 3 over here on the far right. Grade 1, again, something that fully fills the cavity. Grade 2, moderate defects, but not the worst job in the world. If I were the rater, I'd probably still go there and say, ideally we'd want to pull some of these down more specifically. I'd also want to be careful about, are they able to spray insulation over here on the right-hand side or not? Again, grade 2 allows for some defects, a very small amount of missing insulation and a very small amount of compression. Grade 3, again, you may say, hey, well, at least there's insulation there. How's that grade 3? Well, the reason why is because we see that there's missing insulation at the tops of these cavities, and there's just enough compression that ends up making it where basically, the insulation is not going to be in full contact with the air barrier then, being the drywall. And so, this is really a grade 3 right there because it's really not well done. What they should have done is they should have measured those cavities. This is on some type of it looks like a stairwell. They should have measured those cavities, which are obviously smaller than the width of a standard bat, and they should have then cut the bat to fit within those cavities, or alternatively, do something else for the insulation. Blow it, spray foam it, or net and blow it with fiberglass or cellulose, because that would have worked out a lot better in order to achieve a grade 1. Now you can be worse than a grade 3, which would be more than 5% missing insulation, and man, you're really in trouble then. So this crawl space, this is the problem with traditional vented crawl spaces, is it's hard to keep insulation in full contact with the floor above. And it tends to slump away, and over time the moisture in that environment can really cause it to decay and just kind of fall down and become really entirely ineffective. So in a cavity wall system, more or less, having less wood in the wall system is better. Why? Well, because wood does have insulated value. It's about an R1 per inch, but insulation is better. Generally speaking, the average insulation R value is going to be about an R3.5. Could be a little bit more, could possibly be a little bit less, but generally speaking, that's what we're going to get in our insulated cavities. So if we can find a way to have less insulation in those framed wall assemblies and therefore have more insulation in those cavities, we're going to have an overall better performance of that wall system. So that can be done through advanced framing methods, like basically only having single top and bottom plates, having 24-inch on center spacing, having insulated quarters, insulated headers, having insulated interior to exterior wall sections, aka ladder tees. All these things can be done in order to improve the amount of insulation that you have in a wall and reduce conductive heat transfer off of that wall assembly. Or alternatively, if a builder doesn't want to necessarily get fancy with their framing, they just kind of want their framers to do what they've always done, the other option would be to use continuous insulation. If you use continuous insulation, basically that goes over both the cavity as well as the framing, and that allows you to basically, very substantially reduce heat transfer on the very outside of the building assembly, generally speaking. And really, in doing so, that again substantially cuts down on that heat transfer, because now you've got insulation on the outside of those studs, so that you basically reduce the heat loss off of that stud wall cavity. You could achieve this with various insulation board materials, so polyisocyanurate, EPS, XPS. Those are all options. In attics, you could go ahead and blow over the ceiling joists. Gets pretty tough when you're doing with bats, not impossible, but it gets a little bit trickier. But if you just do blown assemblies in attics, then it becomes a lot more easy. Other things that people do with walls would be like double stud walls. A double stud wall basically is two framed walls that are densely packed generally with insulation. And so then your exterior, which tends to typically be the load bearing portion of the wall, tends to be basically, set back from the interior wall, the non-load bearing portion of the building enclosure, in order to basically have a thermal break between inside and outside, which then essentially becomes a form of continuous insulation. Different insulation products used for continuous insulation: EPS foam, that's kind of like your beadboard, kind of like your styrofoam cooler kind of insulation. XPS is the blue and pink board. Generally speaking, polyisocyanurate is generally speaking around an R6.5, but it depends on the blends you get. You get a little bit higher or a little bit less. The various manufacturers make them. They make it in foil faced, non-foil faced, etc. Mineral wool board, so that's becoming more popular. I'd say Roxol or rock wool insulation or Thermafiber. They actually make a board-based product that can be installed on the exterior of the home. And the nice thing about that is not only are you reducing conductive heat transfer with continuous insulation, but then you have more of a fireproof barrier on the outside of your house. Insulated concrete forms, that's a mass wall assembly that uses EPS forms that then basically you fill full of concrete. And so you've got insulation on one side, insulation on the other side. And so basically that gives you continuous insulation on both sides of that concrete wall. Double stud walls, we talked about that a little bit. SIPs, that's a structural insulated panel. That's basically, where you've got OSB on one side with a gummy center of foam, and then OSB on the other side. And so you can more or less stand those up, and those are continuous insulation products inherently. So let's get into a little bit about different specific enclosure assemblies. So attics, arguably the most important place to get right with air sealing and insulation. It's also one of the easiest places to stack up a lot of R value. That's why codes tend to call for higher levels of R value in attics. So like in Michigan right now, the current 2015 IUCC with Michigan amendments would call for R38 insulation in climate zone 5, and then R49 in climate zone 6 and 7. We can do vented attics, which means that there is actually venting, to the exterior, usually through a combination of eave vents as well as some amount of roof venting, and then unvented attics, which is exactly what we're saying, basically, where you don't have venting. Generally speaking, that's going to occur with a sealed attic. So generally speaking, spray foam, although you can use other insulation materials such as a net and blown type of assembly, possibly. All you want to basically make sure that you consult with a good building scientist on dew point calculations so you don't unintentionally cause a moisture issue in a net and blown unvented attic assembly. Flat roof type of like commercial or multifamily buildings, generally speaking, those are all going to have foam board on top of the roof deck, and therefore they are sealed unvented attic spaces. So, again, we want to have air sealing done first. So for some reason, years and years and years into this whole thing, I've been in this, career path for 16 years, and I still see people not air sealing attics. They're not sealing wire penetrations or can lights or electrical boxes or bath fans. We're still not getting those details right. We're not sealing top plates. Folks, you got to have that in order to have the insulation in the attic perform properly. But we'll talk more about air sealing next week. Regardless, big reason why in vented attics, we've got higher R values is because we just have space for it. But you have to have sufficient depth, particularly over the top plate. You want to make sure you got enough, area in order to have insulation over that top plate. So that we're reducing heat loss off the corners of our wall assemblies where they meet the attic. And then we don't want to block any venting, so you want to make sure you have eave baffles. Otherwise, we may have an issue of what's called wind washing, where basically the wind can blow through those soffit vents and blow away the insulation, making it not only less effective because wind is passing through those supposed to be trapped air spaces, but also because it literally just blows the insulation out of the way and no longer insulates certain portions of the house. Unvented attics, again, generally done with spray foam, but here's an image where we're actually showing someone netting and blowing an unvented attic assembly. Probably if they're doing that, you're going to have some kind of foam board on the outside of the roof deck so that you reduce dew point. Again, you can run into moisture issues potentially if you do this type of assembly wrong. So be aware of that and make sure that you're consulting properly with builders and installers so that we don't end up causing an unintended moisture issue. Wall assemblies here in Michigan, we have basically prescriptively R19 cavity or R13 plus 5. And then in basement walls, R10 continuous or R13 cavity. Above grade walls are going to also include like our band joists. They're basically included as the same kind of principle. Big thing here is that we want to figure out what type are we using, what's the R value, how is it being installed so that we assign the appropriate grade. And then, is there continuous insulation? This assembly shows a combination of 1.5 inches of rigid, probably foam board insulation with then cavity insulation. Doesn't say what kind it is, but could be bats, could be blown, whatnot. So it's a combination for this assembly. Again, rim and band joists kind of treated like an above grade wall. They're the vertical plane that separates floors that end at the end of the floor joists. Spray foam is very popular for this because it kind of gives you the benefit of making sure that insulation is fully in contact with that rim board. And then it can also provide air sealing because there's a lot of places where this can kind of leak and cause air leakage and comfort issues. Technically, you could use bats, but it's, as we can see, I would probably call that a grade 3 install because it's really not fully filling that cavity. It's kind of sloppily installed. That's the problem with bats and rim joists. Potentially, you're asking for moisture issues, over time because bats are not moisture tight, generally speaking, unless they're installed with a craft face, and that becomes pretty tricky to do in a rim assembly. Mass walls, less popular here in Michigan, but not unheard of. mass walls in Michigan, generally speaking, we're looking at ICF construction. The value of ICF is maybe you have a little bit less R value, but you have more thermal mass capacitance. And that's a whole other world of building physics. But basically, stone or masonry type of products, they have more ability to be able to store and then slowly release its stored heat energy. So they kind of act as a buffer. They're not insulation, but they're more of like a heat sink and storage mechanism so that maybe you don't need quite as much insulation. Let's take a look at this EPS. Let's just say that that's 2.5 inches on each side. That's R5 total. And we've got maybe R4 per inch for EPS. So it's an R20 continuous. That's not so shabby, really. Add in the concrete. Yeah, concrete's about 0.1 R value per inch. So maybe you got 10 inches of concrete. So maybe, it's an R21 continuous. That's not half bad. But the big value with an ICF, again, is that it stores that heat energy. You could do other things other than ICF. You could just have a poured concrete wall with continuous insulation on the outside. You could have concrete block with continuous insulation on the outside, some type of stone assembly, brick, rammed earth, adobe. These are all different sort of solutions for thermal mass. Tends to be less important here in Michigan just because we really do need more insulation given our long winter seasons, and we're a little bit less sunny. Thermal mass tends to really give you more benefit in places like the Southwest, where it's sunnier and there's what's called a lot of diurnal swing. But wow, now we're really getting into nerdy stuff, and I got to keep going. So let's go ahead. Below grade walls, they are actually, generally speaking, a form of a mass wall assembly. Part of why they need less insulation, they're also below grade, and so the ground is 55 degrees year round, generally speaking, so there's a little bit less heat loss to the ground. Generally speaking, for basement and crawl spaces that are conditioned, you're either going to see continuous foam board on those walls, or you might see a framed wall assembly that has cavity wall insulation. For framed floors, so like say a framed floor over a garage or a framed floor over a ambient space like a cantilevered floor, we're wanting to see an R30, and then with slabs we are going to see in climate zone 5 R10 around the perimeter of slabs down 2 feet, or in climate zone 6 and 7 down 4 feet. So getting into what is in the energy code currently in terms of requirements for insulation, because we could talk all day. We could talk about insulation. You ever want to go above and beyond what we talked about today? I'll talk some shop on insulation. There's a lot to talk about, all different types of products, all different types of opportunities. But I think what we need to figure out is what do we need to do today in order to meet code, and then how do we go above code? So today in Michigan, we have, a R38 in ceilings in climate zone 5 and R49 in the rest of the state. So if you're downstate, R38, if you're upstate, R49, basically, prescriptively. This is prescriptive code. Now, we don't have to follow prescriptive. We could follow performance path, but this is just showing your prescriptive values. For wall assemblies, basically throughout the entire state, an R20 cavity or 13 plus 5, and then basement walls would be an R10 continuous or 13 cavity, again downstate, and then the R15 cavity or R19 continuous when you get upstate, sort of above Clare, where we go into climate zone 6, and then up in the UP, there's a small sliver of climate zone 7 as well. So this just shows you the equivalent U factor for the assembly. This is more relevant if you're doing what's called a UA calculation, a total UA calculation, which would be used for energy code purposes. So doing a total UA calculation, this would be summing, the walls plus the roof plus the floor plus below grade walls. You've got your square foot times the U factor of that assembly. That gives you your U times A, or the UA. And so we've got the as-built home comes out at 173.5 versus the Michigan Energy Code comes out at 174. So we're lower than the Michigan value, the code value, which is good because ultimately we want to have a UA that's lower. Why? Because U factors, the lower the number, the better. So when you have a U value times the area, the lower number is the better. We want a UA value that is lower than the code reference. So how did this work out? Well, our wall assemblies were better, had a lower U factor than code, whereas our roof was not. It wasn't as good. And our floor was the same, and our below grade walls were the same. So basically, we traded off better walls for a worse roof assembly in this particular instance, but it still pans out for prescriptive code compliance following the total UA approach. Now, here in Michigan, a lot of builders are using HERS raters in order to go for the simulated performance alternative. And the reason why is because these are the same two homes. On the left, we see that the home meets the performance requirements by 17.5%. But on the other side, we see a home that is not meeting performance, basically. So you're seeing both as an option, more or less. So one that meets and the other one that doesn't meet. But what's interesting here is that you can actually have a home that doesn't meet the insulation levels either, and still meets performance code compliance. So in this slide, frankly speaking, doesn't really depict that, but that's what the intention is to say you could have a home that doesn't meet prescriptive R value or U factor or total UA requirements, but can still meet code using a performance basis. So jumping into above code programs. So the first program, it's not really a program, but it is if you're working with DTE and Consumers. If you are a partner with DTE and Consumers through their residential new construction programs, you can get an incentive for having your home rated through the HERS process. And if you were here 2 weeks ago, we talked about HERS ratings. Basically, it's a system that's promoted by ResNet, where it's a scoring methodology for the home, and the lower the number is better, ultimately. For participating in a DTE and Consumers Energy's HERS program, you need to score a 59 for consumers or a 60 for DTE. Now, what's interesting about this is there is no hard insulation requirements to get a HERS score. So basically, you don't have to meet prescriptive code insulation levels to still get to that 60 or 59 level to participate through the utilities. It makes it easier to get there if you have a well-insulated home. And obviously, we've talked about the merits of better insulated homes tend to be more comfortable, and they have some other benefits ultimately for consumers and really for grid management. They make them more resilient when we have less heat loss off of them. Nevertheless, with the HERS rating considers not just our insulation levels, but it considers how airtight the home is, how good the ventilation performance is, our heating and cooling and water heating system performance, lighting and appliances. So all of those things are included within the HERS rating. So as a builder, say you want to have better mechanical equipment, but you don't necessarily want to insulate the home in excess, that's an option. You have an option to basically choose instead to just go for a better HVAC package, but perhaps not the best insulation package. You can still get there with the HERS approach. With Energy Star, which is kind of our first step above HERS ratings, again, we talked about this a couple weeks ago. There's a few different versions of Energy Star that are worth talking about. We're going to focus particularly on single family homes because that's where most of our incentives are based with DTE and Consumers Energy. So version 3.1 is the program that is in effect for Michigan today. So if you want to get an incentive through DTE and consumers, or otherwise just label your home as Energy Star in Michigan today, you have to at least meet version 3.1. If you want to meet the 45L federal tax credit, then you have to meet either version 3.2 or 3.3. And then there's a bonus incentive program going on with Consumers Energy through the end of the year for Energy Star Next Gen, which is an all-electric program. You have to basically meet version 3.2 or 3.3 to participate in that program. For version 3.3, the installation levels have to be equivalent to those from the 2009 IECC. And so you have to have basically a decent building enclosure that meets at least the 2009 IECC levels in order to participate in Energy Star version 3.1. Again, there is the ability to use a UA option to trade some of that off, but ultimately you have to have a decent enclosure. It has to meet at least the 2009 IECC level, which is pretty close to what we currently have for the majority of the state of Michigan anyways, especially climate zone 5. We're closer to the 2009 IECC levels of insulation requirements than we are an advanced code. So here's an example of one of those UA calculators where we meet it exactly on. Well, how did we do that? Well, our home, it was built precisely to the 2015 Michigan Energy Code in climate zone 5. Fancy that. This is exactly what I was showing. Ultimately, is that, basically if you build your home meeting this approach, then ultimately, if you meet the 2015 prescriptive values, then you're going to be meeting the 2009 IECC values and therefore, meeting that UA calculation. For insulation to meet version 3.2 of the program, now you have to get to the 2021 IECC levels of performance. And the 2021 IECC, it's an advanced version of code. Sure, people have heard some rumors about its possible implementation here in Michigan. We are still waiting on final confirmation about if and when that's going to happen, and we will keep you posted once we know. But here's how this shakes out. If we have to basically then build, to those levels of performance. So here we go. We've got, a equivalent wall value, an equivalent roof value, slightly better floor value, and equivalent below grade wall value, and therefore we have a UA that is better than it. So that's how you would go ahead and show compliance using the UA methodology in 2021 IECC. Again, Energy Star Next Gen requires that you meet version 3.2, and so basically you have to meet 2021 levels of performance. Now there is the option to also switch over to the more advanced version 3.3, which allows compliance with the 2024 levels of insulation, and there is some moderate adjustment for basically being able to trade off some insulation using version 3.3. So both for tax credit as well as for next gen, you may want to look into version 3.3 if you're working with your builders, because there is a way to get basically 15% less ultimately than what the UA would be for the equivalent of 2024. So there's a little bit more trade-off versus version 3.2, which is very strict at that 2021 level of performance. Energy Star requires grade 1 insulation if you don't have cavity wall insulation. If you have if you don't have continuous insulation, if it's just cavity, you have to have grade 1. If you have continuous, then you can have grade 2 insulation plus continuous insulation. For zero energy ready homes, basically you're meeting version 3.2. And so as a result of meeting version 3.2 of Energy Star, you have to meet the 2021 IECC levels of insulation. Getting into passive house. So again, there's two different passive house programs that one might certify under. There's FIAS and there's the Passive House Institute, which is a German-based organization that does have satellite, basically certification bodies here in the United States. With Passive House, there's really a higher level of focus on building insulation. Why? Well, because ultimately we're really trying to just smash the heat loads so that you practically don't need to heat the home. Through basically just people living inside the home, the internal gains from people, pets, lighting, appliances, those types of losses, plus solar gain coming in through windows, that's almost enough to basically heat the home for free. Now, look, passive houses also do have space heating systems. They do, in fact, get heated almost always. You don't see passive houses that are unheated. That being said, the idea is that instead of having heating be, say, 60% of our energy budget, as it is in a conventional home, it ends up being, 10 to 15% of our energy budget. So how we do that is typically higher levels of insulation that really reduce heat loss, and in particular, continuous insulation layers, as well as more thoughtful approaches to reducing thermal bridging. So thermal bridging through stud wall assemblies, and then through whether or not maybe we have balconies or something else that attaches to the home. Those can potentially also cause there to be a thermal bridge that needs to be accounted for. So doing as much as possible to reduce thermal bridges off of our building enclosure is 100% the critical requirement for passive house, as well as, generally speaking, higher levels of insulation. How high? Well, it depends on where you're building. And you're allowed to go prescriptive for passive house, at least for FIAS, as well as a performance using a special energy modeling program called WUFI. Or for PHI, there's a program called the Passive House Planning Package, aka PHPP. So how much kind of depends on where you're at, but think about code levels of insulation and come close to doubling it. And that's about where you're going to be in terms of the insulation requirements for passive house. You may say, well, man, I really want to know more about passive house. Now you got me excited about all this extra insulation in passive house. Well, guess what? You're going to have to wait. We're going to have whole sections of these trainings specifically on passive house later on in this webinar series. But for now, we're going to wrap up what we've done today. I know it was a big drink of water trying to get through all this information on insulation. You may feel like you're missing some details. How do I specifically implement it for Energy Star? Or how do I specifically implement it for zero energy ready homes? Or again, for passive house? That's okay. This was an overview of insulation. We're going to be getting into those more specific granular details relating to all these above code programs later on in the webinar series. So for today, we're going to go ahead and wrap up what we've done. I really appreciate everybody's time and attention. I'm more than willing to take any questions. If not, we'll plan to see you back here next week for the air sealing and air barrier presentation. Because again, you have to have an air barrier if you're also going to have insulation in order to make a complete building enclosure. Okay, well, thank you very much. Again, happy to take any questions that anybody may have. I don't see any in the chat currently, but I'm happy to take any questions that anybody does have. Okay, well, seeing none and us kind of wrapping up here a couple minutes early. I appreciate your all's attention and participation, and we'll see you next week. Thank you very much.